Hello all, my name is Ragam. I am Assistant Professor, Department of Electrical Engineering, Rajagiri School of Engineering and Technology. Today we will be discussing the second half of Module 4, which is a virtual instrumentation system. It consists of the architecture of virtual instruments, comparison between virtual and traditional instruments, and the concepts of graphical programming. Traditional instrumentation. Traditional hardware instrumentation systems are basically made of predefined hardware components such as digital multimeters and oscilloscopes, and they are completely function specific. And because of their hard-coded function, their uses are very limited. That is, their versatility is limited compared to that of a virtual instrumentation system. With virtual instruments, it is possible to build measurement and automation systems that suit the specific needs of the user, that is, it is user defined, instead of being limited by the traditional fixed function instruments which are vendor defined. Virtual instrumentation is the use of customizable software and modular measurement hardware to create user defined measurement systems called virtual instruments. The simulated physical instruments are known as the virtual instruments. The primary difference between hardware instrumentation and virtual instrumentation is that software is used to replace a large amount of hardware. The software also enables complex and expensive hardware to be replaced by the already purchased computer hardware. Thereby, engineers and scientists can create user-defined systems that meet their exact application needs. And the front panel control function of the existing instrument is duplicated through the computer interface. The applications ranges from simple laboratory experiments to large automation application. And the flexibility is possible here as the virtual instrument capability depends very little on the dedicated hardware and a customer can use his own computer. The history of virtual instruments can be traced from the late 1970s when the microprocessor technology came into existence. The microprocessor technology enabled the machine's functions to be easily changed by changing the underlying software. The development of virtual instrumentation can be classified into 4 phases. The first phase was represented by the analog measurement devices such as oscilloscopes. In the second phase, instruments started to digitalize the measured signals, allowing digital data acquisition and processing. In the third phase, the measurement instruments became computer-based. And the fourth phase represented the development of distributed virtual instrumentation systems. A virtual instrument is composed of the sensor module, the sensor interface, processing module, database interface, user interface, medical information systems interface. So there are 6 sub-blocks in a virtual instrument. So this is basically the architecture of a virtual instrument, and it contains the 6 sub-blocks which we have mentioned in the previous slide. The sensor module, as you know, it will detect the physical signal and transforms it to electrical form. It will condition the signal and then it will transform into a digital form for further manipulation. And through the sensor interface, the sensor module will communicate with the computer. Once the data are digitized, the computer, it can be processed, mixed, compared, or manipulated and stored in a database. The data then may be displayed or converted back to analog form for further process control. First one is the sensor module. The sensor module will detect the physical signal, transform it into electrical form. It will condition the signal and transforms it into a digital form for further manipulation. The sensor module interfaces a VI to the external, that is mostly the common analog world, transforming the measured signals into a computer readable form. The next table summarizes some of the often used human physiological signals. A sensor module, principally, it consists of 3 main parts: the sensor, the signal conditioning part, and the analog to digital converter. So, the function of a sensor, it will be detecting the physical signal from the environment, and if the parameter being measured is not electrical, then the sensor must include a transducer to convert the information into an electrical signal. And According to the position of the sensor, if the application is in biomedical field, the sensors can be classified as implanted sensors, on-the-body sensors, and non-contact sensors. Implanted sensors are those ones which are located inside the body, for example, used for intracranial stimulation. On-the-body sensors are usually the biomedical sensors, such as those sensors which are used for ECG or EEG electrodes. And non-contact sensors are optical sensors and cameras which do not require any physical contact. The signal conditioning module, it will be performing the signal conditioning prior to the analog to digital conversion. It can be any of the signal conditioning functions like amplification, excitation, linearization, isolation, etc. The ADC will change the detected and conditioned voltage into a digital value, and the converter is defined by its resolution and sampling frequency. As you know, the Nyquist sampling frequency is very important as far as an ADC is concerned. The sensor interface. In computing, an interface can be defined as a shared boundary across which two or more separate components of a computer system can exchange information. This exchange can be between software, computer hardware, peripheral devices, humans, or a combination of these. Some of the computer hardware devices, they both send and receive information, whereas some will provide an interface to send the data to a given system. Many interfaces are used for communication between sensor modules and the computer, and they are classified based on the type of connection into two, wired and wireless. Wired interfaces are standard parallel interfaces. The general purpose interface bus, the small computer systems interface are some of the examples. Next one is a wireless interface, which commonly make use of Bluetooth or the GPRS or the GSM interface. It is mostly suited for the implanted sensors where wired connections are not possible. It will also reduce the installation cost and create plug-and-play like network of sensors. For communication with medical devices, standards are set by IEEE, like the IEEE 1073 standard. Also, they are highly robust in an environment where devices are frequently connected to and disconnected from the network. Device miniaturization also allowed the development of personal area networks of intelligent sensors. The processing module. Integration of microprocessors and microcontrollers allowed flexible implementation of the sophisticated processing functions. Functionality of the virtual instrument, as you know, depends very little on the dedicated hardware. Processing functions used in virtual instrumentation can be divided into two. One is the analytic processing and the second one is the artificial intelligence techniques. Analytic processing. It defines clear functional relations among the input parameters. Some of the common analysis used in VI are spectral analysis, filtering, windowing, peak detection, etc. Virtual instruments often use these various statistic functions. Most of these functions can now be performed in real time. Artificial intelligence techniques. Artificial intelligence technologies can be used to enhance and improve the efficiency, capability, and features of instrumentation in application areas related to measurement, system identification, and control, as these techniques exploit the advanced computational capabilities of the modern computing systems. Artificial intelligence technologies such as neural networks, fuzzy logic, and expert systems were applied in various applications, including sensor fusion to high-level sensors, system identification, prediction, etc. Various nonlinear signal processing techniques like fuzzy logic and neural networks are commonly used tools in the analysis of biomedical signals. And using artificial intelligence, it is even possible to add medical intelligence to ordinary user interface devices. As an example, several artificial intelligence techniques such as pattern recognition and machine learning were used in software-based visual field testing system. A visual field test is an eye examination that can detect any problems in the central and peripheral vision, which can be caused due to various medical conditions such as glaucoma, stroke, brain tumor, or any other neurological defects. The database interface. Computerized instrumentation allows measured data to be stored for offline processing or to keep records as a part of patient monitoring. And majority of the database interfaces uses the DBMS interface, that is the Database Management Systems interface. It provides efficient management of data and standardized insertion, updation, deletion, and selection of data. The DBMS provides the external SQL interface, that is the Structured Query Language interface, for enabling transparent execution of these programs. Also, some of the other interfaces used by the virtual instruments are as indicated in the next table. Next one is the Medical Information System interface. Virtual instruments are increasingly integrated with other medical information systems, such as the hospital information systems, especially for patient monitoring. And they can be used to create executive dashboards, supporting decision support, real-time alerts, and predictive warnings. Some virtual interface toolkits, such as LabVIEW, provide mechanisms for customized components, such as ActiveX object. An ActiveX object creates a reference to an object that is connected to another application or a programming tool. In web-based telemedical applications, this integration is usually implemented using URL, that is a Unified Resource Locator. Each VI is identified with its URL, receiving configuration settings via the parameters. The virtual instrument can then store the results of the processing into a database identified with its URL. Next one is presentation and control. An effective user interface for presentation and control of a VI affects efficiency and precision of an operator who does the measurements and facilitates the result interpretation. Since most of the computer's user interfaces are much easier shaped and changed than conventional instruments user interfaces, it is possible to employ more presentation effects and to customize the interface for each user according to the application. So, according to the presentation interaction capabilities, these user interfaces can be classified into terminal user interfaces, graphical user interface, multimodal user interface, and virtual and augmented reality interface. First one is the terminal user interface. The first programs for instrumentation control and data acquisition systems had character-oriented terminal user interfaces, as the earlier general-purpose computers were not capable of presenting the complex graphics. And the terminal user interfaces require very little of the system resources. They were implemented on many platforms. Although the terminal user interfaces are now not widely used on desktop PCs, they have again become important in a wide range of devices like cell phones or low-end PDAs. Next is the graphical user interface. Graphical user interfaces, otherwise known as GUIs, they made the human-computer interaction more easy, thereby making the virtual instrumentation more accessible. And because of the simplicity of interaction between the human and the computer, it made possible for the creation of user-friendly virtual instruments. GUIs allowed the creation of many sophisticated graphical widgets such as graphs, charts, tables, gauges, meters, etc., which can easily be created with many user interface tools. An example of a graph created using VI is as shown below. Multimodal presentation. So next, third one is the multimodal presentation. So in addition to graphical user interfaces that improve the visualization experience, contemporary personal computers are capable of presenting other modalities such as sonification or haptic rendering. Sonification is the use of non-speech audio to convey information or perceptualize data, something like the sound of handwriting, or another example is the rate of clicking of a Geiger counter, which convey the level of radiation in the immediate vicinity of the device. Second one is haptic rendering. Haptic broadly refers to the touch interactions that occur for the purpose of perception or manipulation of objects. These interactions, it can be between a human and a real object. And rendering refers to the process by which the desired sensory stimuli are imposed on the user to convey information about a virtual haptic object. So, overall, haptic rendering allows the users to feel virtual objects in a simulated environment. Multimodal combinations of complementary modalities can greatly improve the perceptual quality of these user interfaces. Next one is virtual and augmented reality. A combination of virtual presentation with real-world objects creates augmented reality interfaces. For example, augmented reality may allow computer-generated tumor image from MRI recording to be superimposed on the real view of the patient during surgery. This is an example for a biomedical application. This is an example of a sensory model. In this model, the analog signal is sensed by the sensor module. The analog signal can either be any type of signal. If it is a biomedical application, it will be an ECG signal or an EEG signal. And the sensor module will be sensing the signal, it will be digitizing the signal and will pass through the sensor interface, and then it undergoes 2 levels of signal pre-processing before it reaches the end user or the application. And the second optional pre-processing stage is present for the integration of complex processing mechanisms into the virtual instrument solution. These are the advantages and disadvantages of VI. Next one is a comparison between the traditional and virtual instruments. Next is a graphical programming concept using LabVIEW. LabVIEW stands for the Laboratory Virtual Instrument Engineering Workbench. It is a programming language, or it is a graphical programming language, capital G, that uses icons instead of lines of text to create applications. That is, instead of writing code, we will be using the graphical programming methods. And the LabVIEW programs, they are known as the virtual instruments because their appearance and operation imitate physical instruments like the oscilloscopes or the digital multimeter. LabVIEW consists of a set of virtual instruments and functions for acquiring, analyzing, displaying and storing the data. And also it includes many analytical functions. And also there are tools to represent the data on computers in many forms. So as I have said, the LabVIEW programs are called the virtual instruments, and each VI has got 2 components. One is the front panel, that is the user interface of VI, and it has got controls for input and indicators for output. Second one is the block diagram, the accompanying program, which is in the form of graphical representation of functions, which is used to control the front panel. And here in the block diagram, the components are wired together. The front panel is a user interface of VI. In the front panel, there will be controls and indicators in which the interactive input and output terminals of the VI are present. The controls are knobs, push buttons, dials, anything, and the indicators can be graphs, LEDs or any other display. The controls will simulate the instrument input devices and supply data to the block diagram of the VI. Indicators will be simulating the output device and display data the block diagram acquires or generates. So this is an example of a LabVIEW front panel. You can see many types of displays over here. Next one is the block diagram. In a block diagram, every control or indicator on the front panel has a corresponding terminal on the block diagram. It contains terminals, nodes and wires, as you can see in the diagram. Wires will be connecting each of the nodes on the block diagram, including control and indicator terminals, functions and structures. And tools palette. Tools palette is available on the front panel as well as in the block diagram. A tool is a special operating mode of the mouse cursor. When you select a tool, the cursor icon changes to the corresponding tool icon. and using the tools to operate and modify the front panel and block diagram objects. The control palette is available only on the front panel. The control palette contains the front panel controls and indicators which are used to create the user interface. The function palette is available only on the block diagram. The function palette contains the objects you use to program your VI, such can be arithmetic, instrument, file or data acquisition operations. Examples of some type of controls or indicators are as shown. An example of a data flow programming. You can see there are two numbers which are added and then it is subtracted with a random number. And the second one, you can see two numbers are added and their sign is displayed as a result. VI virtual instrument that can be used within another virtual instrument is known as a sub-VI, and it is analogous to a subroutine. The icon is a VI's pictorial representation and is used as an object in the block diagram of another VI. And a VI's connector is the mechanism used to wire data into the VI from other block diagrams when the VI is used as a sub-VI. And these are some of the conventional language terms compared with that of a LabVIEW terms. Thank you. An example of a LabVIEW model is as shown. Here the function is to compute the hypotenuse of a right angle triangle. In the front panel you can see there are two inputs which are A and B, and C is the output. And the actual programming that happens in the block diagram. In the usual programming languages, lines of codes are written, whereas in LabVIEW you can see the lines of code are replaced by the icons. So here the two numbers A and B are inputted by the user. And the block diagram, the two numbers are squared, their sum is found out and their square root is found out, and the final result is given to the block C. So in the front panel you can view the result at C. Thank you all.